And okay, so let's get started with the class material then for today. Okay, so this quote, which always gets misattributed to a bunch of folks, either Yogi Berra or a few others, it really summarizes the class, which is prediction is hard, especially about the future. And when people usually quote this, and when Yogi Berra, whoever said it, originally said it, probably meant it as a joke that, like, of course, all prediction is hard. And so, I mean, like, all prediction is about the future. And so what does it mean when you say prediction is hard, especially about the future? But funnily enough, I think sort of the theme of this today's lecture is that most machine learning tasks that y'all are like, learning in applied machine learning or, have learned in the past, that machine learning is very, very good at, although we call it prediction, is not about the future. And in a lot of these, socio-technical systems or people-driven systems or whatever you call them that we've been talking about in class, you actually do need prediction about the future, and that ends up being harder and impossible. And so today's class is about the limits of prediction. And then maybe the second motivator is this XKCD comic, which I'll give you all a few seconds, but it sort of, the punchline is, especially to an outsider, it can be really hard to explain what makes a task easy versus impossible, right? So like, given modern technology, okay, so I mean, so this XKCD is about 5 years old, or maybe like 8 years old already. So actually the sort of even the second task of checking whether a photo is of a bird is essentially solved today. And so, they don't need to research team in 5 years anymore, they can do it today. But at least 8 years ago, using technology from then, it was trivial to check where a photo is, but it was much harder to check whether the photo is of a bird. And to lay people, this difference can seem kind of like arbitrary, and it can be really hard to explain. And so like maybe another theme, and not just lay people, but also like, some of y'all, like, or like, me sometimes distinguishing what makes a prediction task easier or harder. And because of that, sort of there's this term that a professor who I'll mention in a little bit likes to use called AI snake oil, which it's very easy to fool people into thinking that AI is much better than it is. And a lot of these tasks, what even like common sense would suggest that like this task is just impossible. And so sort of a second theme of today's lecture is to sort of one, just try to be a little careful about what, try to apply, I don't like the term common sense too much, but maybe common sense reasoning of, is this task that I'm about to do that I'm, appealing to AI magic? Is that even something that like anyone could reasonably think is possible? Or also be careful when you're selling these technologies, is that you're not, becoming a sort of a snake oil salesperson. Okay. Okay, so the sort of the first big example in the class is going to be I'm going to walk through this paper, which is sort of appeared in PNAS last year. And it was led by Matthew Salganik, and he's a professor at Princeton. But it was a collaboration of hundreds of researchers, hundreds of machine learning researchers. And so like the author list is incredibly long. And so what was the paper title? So the paper title is Measuring the Predictability of Life Outcomes with a Scientific Mass Collaboration. And so what was the research question? The research question is, how predictable are people's life trajectories if you have a bunch of data about someone's early childhood, right? So I give you a bunch of data about people from ages 0 to 10, and then ask, what does their life look like when they're 15 years old? And how good can you get at that task? And the way they sought to answer this question is what's called the common challenge methodology. which is the following. This is essentially a Kaggle competition for those of you who've done that. But it's what it is you give a bunch of researchers the same data and the same task, and then see how they perform in predictions, right? So you don't just have your research team try to do this prediction task, but you like post the data online, you allow anyone to, or maybe in their case, they only gave it to some researchers, but or like, a team of like a set of 500 researchers or something, I'm not exactly sure, but you give it to a bunch of researchers and then you let them all compete on see how good their predictions can get. And the reason they did this common task methodology is, what if there was only one research team who tried this task? And what if the answer was that, oh, we aren't very good at this task? Then a natural response by like any reader or a reviewer or anyone reading, just anyone, is what if that team was just bad at machine learning? Like, how do I have to like, why do I have to trust that this team was good at machine learning, or that the methods that they use were actually the right methods, right? What if they had used some other method? Would they have done better? And this common task methodology gets around that because you have hundreds of teams, hundreds of researchers trying all sorts of methods. And if all of them do poorly, then you can be pretty sure that it's like something about the underlying task that's hard, as opposed to the people doing it. And this gets around what's also called the file drawer effect in research, which is in social science, I mean, it's getting better, but historically, and even to some extent now, it's extremely hard to publish negative results. So it's like, if if they tried to do this and their finding was, oh, it's not predictable, then like it's hard for like some journal to accept the paper just because it's, sort of negative results aren't considered publishable. And this task methodology gets around that because even a negative result makes now like a strong result that doesn't, like, you don't have to like trust them being good at machine learning and things like that. Okay. So, okay, so what was the data set? The data set that they had was following what's called the Fragile Families and Wellbeing Study. And so this study has been going on since the year around 2000, and which follows about 5,000 families who each reside in a large US city. And each of these families gave birth to a child or welcomed a child into their family around the year 2000. Actually, I do think it's giving birth as opposed to just like adoption, but I'm not sure about that. I can check and look, but the paper was careful to use the give birth language. Okay, and so okay, so you select these set of families around the year 2000, and then you collect data on each of these families when the child was 1 year old, 3 years old, 5, 9, and 15. And this is extremely rich data set that they collect. So they of course have a bunch of background data on each family, like demographics, geography, just like all sorts of like the standard background characteristics. But then each of these years, you collected that data again, but then you also did interviews with the parents, teachers, starting age 9, I believe, maybe age 5, they started interviewing the child themselves. The researchers did home visits for each of these families. And I just put this up there, but like I just want to emphasize like how rich this data set is. Like anything you could possibly want about a kid is in this data set. So information on attitudes, relationships, parenting behavior, demographics, physical and mental health, economic and employment status, neighborhood characteristics. The child was interviewed, and then the interviewer coded them on a bunch of characteristics. And then you have you coded how the child has family relationships, what they do at home, do they have friends, just like all sorts of things. And then during the home visits, the person visiting the home also collected a bunch of information like quality of housing, nutrition, healthcare, like clothing, like parenting style, literally anything you can think about how a child is being raised that is visible to an interviewer or collectible through data is in this data set. Okay. And then you have all of this data for ages 1 through 9. And then the question is can I predict each of the following things at age 15? So can I predict the GPA of the child in, I guess, age 15 is high school? Some measure of child grit, which is like, grit was all the rage back when the study was being collected. And so it's, like how much like fortitude in some sense does this person have? Whether that child was in a household that was evicted, whether that child was in a household that faced material hardship, whether the primary caregiver of the child was laid off from their job, or whether the primary caregiver of the child was participated in job training. So you want to see if given all those thousands of variables, so you ended up having almost 13,000 variables about each family from ages 1 through 9. And they also gave the researchers a training data set of these 6 outcomes for half the families. And of course, they didn't give the age 15 outcomes to the rest of the families. And then they just did a leaderboard competition for how good people are at predicting the at predicting these 6 outcomes for age 15. Are there any questions about, are there any questions so far? Okay. And just clarify the common task approach a little bit more. Like I said earlier, this is essentially a Kaggle competition, or approximately what we're doing for the class project minus the leaderboard or plus the leaderboard. And so you give the test data set, just the test like covariates to all the researchers. You ask the researchers to predict outcomes for the test data set, and then you host a leaderboard for how good people are doing during the class, during the sort of the competition. And then you also have a holdout set in which you're going to evaluate people at the end. And so everything in white is what you gave people, is all this background data set, and then half the outcome data for age 15, and that was training. And then you held out the answers for the leaderboard and the true holdout set. And then at some point you end the competition, and then you evaluate how everyone is doing on the holdout set. Okay. So I guess questions for the class. How good do you think the predictions were? And so this is on the R² scale. So I imagine most of you have done, run enough regressions or done enough machine learning tasks that like you maybe have some intuition for R². I'm not going to embarrass myself to try to explain in one sentence in lay terms what R² is here, but it's essentially a measure of how good the predictions were. And it's a scale from 0 to 1. And so does someone want to guess, or do people want to guess in the chat, what do we think these R² values were and maybe how they differ for these different tasks? So maybe, maybe one of these tasks is up at 0.75, another one's at 0.6, another one's at 0.9 or whatever. So what are these values? I'm happy to keep pausing here until people say things. Okay, so somebody says probably low for GPA. So what does low mean for you? Okay, and then someone else says in the chat, the link below says snake oil. So probably probably below 2.25 for all of them is the guess. Someone else says 0.18. Someone else says probably low or below 0.25 for grit. 0.75 for GPA, less than 0.5 for everything else. Okay, do we have any more guesses? So the person who said GPA or grit is 0.25, what do you think about everything else? Okay, and then somebody says, sorry, I'm not saying names just because this is recorded. So like, I do recognize that you all have names, but I do not want to say the names out loud because it's being recorded and posted on YouTube and so on. Okay, so somebody says GPA should be predictable. Somebody says eviction is high, maybe around 0.7. Okay, and somebody else says all extremely low. And then the follow-up to my question about below 0.25 for grit, and then sort of the follow-up was that everything else seemed predictable. Okay, and so presumably you mean above 0.25 for everything else. Okay, so this is the R-squared values. And this is for the best, the best team for each of these out of like the 500 researchers that submitted this. So material hardship ends up being, and so I think people were people were directionally correct in terms of relative terms. So like material hardship and GPA were the most predictable, and then grit and everything else was amongst the least sort of had bad R-squared values. And yes, I mean, I just want to sort of point out here is, even though my priming was that sort of this lecture was all about how prediction is hard. And as someone pointed out, the link at the bottom where I got this image from, the talk title is AI snake oil. Even with that suggesting a very low, sort of like that these R-squared values are low, I think people sort of basically no one guessed as low as, or I think I saw a few at the very end, is as low as they really were. I see a question in chat, I'll get to it after I get to this. So not only were essentially all of these values extremely low, basically the fanciest machine learning didn't help. So these green lines were sort of what a 4-variable linear regression picked. And so, subject matter experts were like, okay, out of all these 13,000 variables, I think these 4 variables are going to be the most important. And then a simple linear regression on these 4 variables. And so essentially the fanciest machine learning didn't get you very far, or much further than a simple linear regression got you. And linear regression is a technique hundreds of years old, or at least 100 years old. Okay. And so there was a question in the chat. What is the big difference? Was there a big difference between performance on the held out test set versus the exposed validation set? That's a good question. I don't know the answer for this competition. It is something to, I think, keep in mind in like Kaggle competitions. So like I think this is a good instructional thing. And so let me just go back to the slide. So the way these competitions end up working is there's a leaderboard test set, or sort of, as the chat called it, an exposed validation set. And sort of the people don't see the answers for this exposed validation set, but they do see how well they did. And so you submit you submit your predictions into this leaderboard, and the leaderboard tells you, okay, your current R-squared or your current accuracy is XYZ. And sort of, so they showed that, and then so because that's exposed, people can choose their models, and people can make the next model in order to try to improve this try to improve their leaderboard score. And so because they're doing this iterative thing in which they're choosing new models in reaction to the leaderboard score, you can't use that as a test set. You have to have a completely separate test set that you actually evaluate people on. And so I think what the question was getting at was, you could imagine for this challenge that because you have even more variables than you have training data, you could imagine learning completely you can certainly imagine, without careful regularization, just completely learning the training set, and then but that would do bad on the leaderboard. But then you can imagine people tuning their answers and keep choosing new and new models in order to do better and better on the leaderboard. But that doesn't actually lead to holdout to benefit true performance increase on the true holdout set. So that's a good question. I don't know the answer. At least they didn't report that in the main paper. They might have reported that in an appendix. They probably sent a link to the leaderboard that I didn't click through. Okay. So yeah, so basically all the predictions were bad, and the predictions weren't really much better than a linear regression. And exactly, in hindsight, I regret not asking y'all this, but certainly this is a task that even if y'all had predicted that, the best predictor weren't very good, I'm sure, I think most of you probably would have said that the best predictors were much better than linear regression. That whatever was being predicted was something that just fancy statistics could capture in a way that linear regression can't. And it turns out that's not true either. Okay. And then a few more empirical findings from this paper that I want to highlight, which is, first of all, they used an extremely again, there were hundreds of researchers trying their best. They used every statistical and machine learning model that you could imagine, but they basically all performed similarly. For all the outcomes, the distance between the distance between the two submissions that were farthest away from each other was less than the distance between the best submission and the truth. And then the second thing, this is perhaps far more subtle, something that maybe I wouldn't have guessed but in hindsight makes sense, is that there was a big heterogeneity in how predictable certain families were. And so some families were correctly predicted by all the models, but other families were incorrectly predicted by everyone. And so I think this is a neat illustration. So I think there's a lot going on here in this plot that I just put up. So let's just look at the top. Let's just look at material hardship. And so each row here in this color plot, each row is a team. And so you have a row of pixels, and a row of pixels represents the teams. Each column here is a family. And then the color says what was the mean squared error for that family in that team. And so as you go left to right, and then you order all the families in terms of the highest, sort of from the lowest to highest mean squared error across teams. And so you see on the left, there's some families that basically all the teams were correct on. And as you go to the right, you get to some families that basically all teams were really had really high mean squared error. And then, this is extremely obvious in the job training and the layoff. And so part of what's going on is class imbalance, is that most of the families were not people did not participate in job training and they were not laid off. And so basically as you switch this binary from not being laid off to being laid off, basically everyone's mean squared error shot up. And so I just wanted to put on here is that even if you have pretty good average mean squared error, like even if you're one of these teams and you think, oh, my R squared is like 0.25 for material hardship, I did a pretty good job. It turns out you were actually doing a pretty bad job for a large class of families. And so if you were to actually act on those predictions, you might have been doing you might not have done great. Okay. And so what's the summary here? The summary that I think is that, so this study shows us that predicting life outcomes is extremely hard. And the fanciest machine learning isn't much better than even the simplest models. And so what I hope to sort of talk about a little bit in the rest of the lecture today is, why is this hard? And when, like, can we sort of predict when machine learning methods will fail? And why was what contrasts this prediction of like the fragile families than like places where machine learning has made an incredible amount of progress? So things like, playing Go or chess, or image recognition, or speech transcription, or all of these other tasks that y'all are learning in other classes, that machine learning is magical. So what is different about this task? Okay, and so some of the or much of the next few slides are essentially stolen from this talk by Arvind Narayanan. Arvind is a professor at Princeton. He does amazing research on a whole variety of things, but sort of recently, a talk that he's given in a few places is like trying to combat what he calls AI snake oil. And I think I've linked the video on the course website of his talk, but the next few slides are essentially stolen from his talk, with a little bit of my own commentary added on top. Like this slide is essentially stolen from his talk. Okay, so he categorizes, so like he finds it instructive, and I thought this was actually really enlightening to me, is the sort of this breakdown of where progress in machine learning has happened recently. And so his talk was given this year, and so like recently we mean the last 5 or 10 years. So there's some domains in which there's been an incredible amount of progress. So like reverse image search, or image recognition, or medical diagnoses from scans, speech to text, deep fakes, and this is what I added, right? Like game playing machines, so chess, Go, Atari games, all sorts of things. There's been a bunch of domains in which there's been some progress, but maybe not as much as we would want. And maybe we're hitting some fundamental limitations limitations for how useful this stuff is. And it's unclear whether we'll get much better. And so things like spam detection, detecting whether something violates a copyright, whether we can automatically grade essays, or detect hate speech, or detect misinformation, or do content recommendation. And then there's a large class of things that sort of he calls fundamentally dubious, which a lot of companies, a lot of researchers have tried to sell that, like, oh, we're good at these things. But it's like fundamentally like a hard task. He says it's unclear whether, like, sort of like the current things don't really work very well. And it's like unclear whether they ever can work very well. And this is like, certainly if you believe the fragile outcome stuff, sort of like that's in this class, right? Is like things that just like do not work very well, and we would need some breakthrough in machine learning in order for it to work well. And so like, what is some rough categorization of all of these things? Okay, so a summary. So I'll get to the summary in the chat in a second, but I don't think that's actually just I don't think that's quite the summary, but it's close. Okay, so this first task is things that have an objective ground truth, or what are called perception tasks. Like, we're not actually trying to predict some future. All we're doing is, so like, think about like what image recognition is. There's a real dog out there in the world, and then you take a photo, and a photo is a 2D projection of a dog into, like, you know, so like a 2D space that might have color. And there's no predicting the future. All you're trying to do is, you're from the 2D projection, you're trying to go back to the past and think about which object produced this 2D projection. And so this is a perception task, or what he calls reverse prediction. And then I added this like game playing machines stuff where, you know, in some sense, there's a very clear task of what you need to do. You need to like win this game, and you can simulate trillions of games. And then the things in which there's been some progress is in which we're trying to guess average human judgment, right? So like a machine learning task that's trying to grade essays is trying to grade, it's trying to predict, if a human were to read this essay, if the like, what would the average human judgment be? And then all of these last things are, you know, things about predicting the future. Like, these are true prediction tasks, where I actually am trying to say is, here's everything I know that has happened so far. I want to predict how the world is going to unroll. And although we call these other tasks prediction tasks, they're not actually trying to predict the future. And so I do want to be slightly more subtle here than predicting humans is hard, because sort of in this first thing, in which we have had substantial progress, like chess and Go and video games, in some sense, you are predicting humans there too, right? You need to predict what your opponent is going to play in the next turn. You need to predict what strategy they're, like, you know, what they're going to play 10 turns from now or something. And yet we've made quite substantial progress in that task than in the task on the right. And so I do think you need to sort of think a little bit more than that on what is fundamentally dubious. Okay, and so there's a question in the chat. Would I include something like stocks in there? I would. So I actually did add it there, and then I removed it. I think that's a longer discussion for terms of like what from stocks are predictable and what from stocks are not predictable, right? So like, clearly there's like, you know, many hedge funds that are investing a lot in algorithmic trading, and they're not naive, and they're claiming to make, you know, billions of dollars in algorithmic trading, and so clearly there's something there, but I would argue they're not predicting the future. They're sort of, I mean, a lot of it's like, you know, sort of algorithmic, what's that word? Just like front running, and just like finding, what are those called? Finding sort of like no lose trades and things like that across the market. And so arbitrage, right? Like algorithmically finding arbitrage opportunities and then front running the market. I would say like the actual true prediction of the market is like virtually, like, maybe someone can correct me as wrong, is not really doing very well. And yeah, so, okay, so like what separates these things in which we've had substantial progress to like the fundamentally dubious? Yeah, so let's go through maybe like a sequence of hypotheses, and that like all of these are true in somewhat, but you know, all of these apply to predictions with humans and predicting about humans in the future, but they don't apply in all prediction tasks. They don't apply in all prediction tasks about humans. Okay, and so exactly, before we go to the specific hypotheses, let's go to like the high level things that could be going wrong, right? And these are things that could be like, you know, that could have gone wrong in the fragile family setting. These are things that could go wrong in any prediction setting. So you have methodological limitations. like how much RAM you have on your computer, how much CPU, like literally hardware constraints, algorithmic constraints, right? And it would be really convenient if this was the answer that made all prediction hard, right? Because a lot of these are likely to be overcome eventually, right? Give it 10 years and we're going to have computers. If you believe Moore's law says computing power doubles every 18 months. And so I'm not going to embarrass myself by doing math, but in 10 years, you're going to have what, 16 or something times the number of computing power, something like that. So, right, so give it 10 years and then we'll overcome this limitation. And for many tasks, this has been and will continue to be the answer. And this is what has caused substantial progress on the left. Okay, what's another hypothesis? What's another reason prediction can fail? Maybe you don't have the right measurements or data yet. And we talked a lot about this in the first few lectures of the class. This is slightly less convenient if this is the answer. And that I have to go out and surveil more people and collect the right kinds of data in order to make these prediction things. And you could potentially overcome these things, but we'll likely need to make trade-offs with privacy and cost. And then you have fundamental limitations. You can call this universal noise, you can call this non-determinism, irreducible, right? You could call this all sorts of things, and I'll go through specific reasons you could have fundamental limitations on the left. Fundamental limitations, and I'll start this on the next slide. And this is the very inconvenient answer if you're trying to make money off predictions, because this is saying that you'll never get better, and you simply can't succeed. And the claim is that many predictions with and about humans is in this category. Okay, any other questions so far? Okay, so I'll move on. Okay, so let's dig into this last one a little bit more. Why do some of these fundamental limitations arise? Okay, so the first set of reasons is, and let me just sort of give a whole caveat, is none of this stuff is exhaustive, right? There's a whole bunch of sort of other reasons, I think this is a very nice high level category. And then the other one is, just so Arvind doesn't get blamed for my mistakes. So he sort of started the list of hypotheses in the next slide were from him. And I think this slide was more of my categorization of the list of hypotheses. So don't blame him for the categorizations, maybe blame me instead. But yes, I mean, these set of slides are still coming from him. Or the ideas are coming from his talk. Okay, and so why do some of these limitations arise? And actually now I'm moving from, not just talking about from his talk, but actually a course on limits to prediction. So it's funny, when I started creating this lecture, I thought that I would base it mostly the source material for me was the paper that I just talked through and so on. But then Arvind Narayanan and then Matt Salganik actually created an entire semester-long course around this topic and what are the limits to prediction in different domains and how do they arise? How can we tell the domains in which there are fundamental limits? How can we tell the domains that aren't? I really encourage y'all, if this is an interesting topic, to I'm only touching the surface on the nuance here on how things differ between domains. And okay, so there's a question in the chat. but much of science implies determinism. If you truly believe that, I'm happy to put some money against you on your ability to predict many of these tasks. Okay, so like, why do some of these limits to predictions arise? Okay, so the first one could just be that much of life is like truly stochastic or effectively stochastic when it comes to what we can observe and compute as researchers. And this is like roughly, it's called many things. It's called chaos theory. It's called the butterfly effect. But it's essentially saying that, the first reason could be that you have large outcome changes due to truly small input changes, right? So like the original thing is, like a butterfly flaps its wings near the western coast of Africa, like in the southwestern coast of Africa, and there's a hurricane in the northeast of the United States 2 weeks later, right? That's like that idea. Or you have shocks, right? Like I truly cannot predict who's going to win the lottery if the lottery is done right, right? Like if the lottery, it's truly random, it's not gameable, I can't predict who's going to win. And so I cannot predict the life outcomes of the families. Like if 10 families, if one of them is going to win the lottery. And the claim is that much of life is like this, right? Like who gets laid off when is like a truly stochastic, impossible to predict thing. You could also have fundamental data issues. So you might never hope to collect some kinds of data. So for example, like I think the example that they gave in their pre-reading for the class was like, or maybe I'm making this example up, is like suppose there's some landlord who has a bunch of people late on their rent and like is going to like evict some of those people, and like the landlord is very cynical and doesn't want to evict everyone, but does want to evict some people to teach them a lesson, and they're going to choose arbitrarily, right? Like you can never hope to know what's inside the landlord's head. You can never hope to collect some kinds of data. And then I think this is I actually got this directly from their reading. This is like a cute little illustration. You have the 8 billion problem when it comes to predicting humans, which is at the end of the day, the maximum number of training samples you can get is 8 billion and any prediction task about humans. And this is with all the if you're going to want to predict something for the entire world, as opposed to like, in a small geographic region. And a lot of these prediction tasks, especially with modern deep learning pipelines, use far more than that many samples. So for example, we go back to like AlphaGo and chess and so on. So a professor, I was listening to this talk at, so it's unclear, I think, from like what OpenAI has released about Alpha or Google Brain, whichever one of them did AlphaGo, I forget. I think it was Google Brain. Whichever one of them did AlphaGo, I think they were very cagey about how many games they actually used to train. And there's this reinforcement learning professor at Stanford who I was listening to his talk. I don't want to say his name because I don't want to blame him if I remembered his talk incorrectly. Is he estimated that they gave that they used about 1 trillion, at least 1 trillion games against itself in order to train AlphaGo. Or the number of games they used was in the trillions. And you just don't have that when predicting real things about humans. You have 8 billion training samples at most, or about 8 billion. And then you also have that, you have drift, right? That like the world is changing. And so the mapping from the data to the outcome is changing. And so like the world today looks very different than the world a week ago or a year ago or 5 years ago. And so if you try to use data from 5 years ago, maybe it's not relevant anymore. And then you also have disagreement on the label, right? So many of these things sort of like certainly like, like how good this essay is something that like humans will fundamentally disagree on how good certain essays on. And you have a wide variety of heterogeneity of opinions on various essays. And so how do you sort of get aggregate predictions when even humans will disagree. Okay. And then the last one, which I want to actually focus on for the rest of this talk, because I think it's closer to a lot of the themes in this class, is in a lot of these settings, the machine learning and this is now deviating from a lot from sort of or the rest of this lecture will deviate from what they talk about, what they focus on in their class. But in a lot of these settings, the machine learning algorithm is a player in the game, right? Like is like causing changes in the world. People are reacting to the machine learning algorithm. And so you have all sorts of incentives and feedback loops. You can call it strategic behavior. You can call it all sorts of things that are happening because of the machine learning algorithm. And that's causing distribution shifts. That's causing sort of the predictions to no longer be accurate for these algorithms. Okay, and that's what I'm going to focus on for the rest of this lecture. But before then, I have these links here. There's like I said, there's like, I think they, Arvind and Matt spend an entire semester on this topic, on what's predictable, what's not, what are domains that you can hope to make progress and domains that you can't, and like what separates them. And so like go to their class syllabus. Here I just put up a bunch of papers that they had on their syllabus, talking about like exactly this question in various domains that are reaching, very different conclusions for different domains. Okay, any questions so far? Okay, and yeah, so for the rest of today's lecture, I want to focus on some of this is hinting at what project part 2 is on, which is all about, incentives and feedback loops and competition and so on. And so I just want to give some overview on what are how difficulties can arise when the prediction task is like causing changes in the world. And so this is something from like not quite a machine learning example, but an old school algorithm from the 90s, which this is from Colombia. This is an example from Colombia that launched a social program in which they gave some sort of benefits to people below some poverty index score. I don't actually know what went into I didn't read the paper closely enough, but so I don't know what went into the poverty index score, but it was like an index score that like sort of had a bunch of features about someone's household and then like outputted a score for whether they're in poverty or not. And when they launched this program, so in the early to mid 90s, this is what they designed the score such that you would have a normal distribution, right? So like society looks like this, and then there's some cutoff below which, there's this vertical line below which you get benefits and above which you don't get the benefits. And then what happened is over time, people started gaming the definition of the poverty score so that they could receive benefits. So 2 years later, in 1996, the distribution looked like this. You can tell that it's slightly shifting to the left compared to the 1994 distribution, but maybe it's not that extreme yet. By 1998, you saw this distribution, that people got really good at gaming, and that there was a large set of people just to the left of the eligibility, as opposed to just to the right of the eligibility. And then by 2003, it had completely unraveled. The poverty index score was completely it was no longer an effective score, and that most of the population was now below the eligibility threshold. And the claim is that if you're deploying machine learning algorithms that is similarly, deciding benefits or deciding something that some people get something and other people don't get something, you need to be careful about this type of gaming. And so let's do a second real world example. So some of y'all might have been watching the news in the last few weeks. If y'all watch market news, is Zillow, which is a home buying, which is an online sort of platform that you can see home prices. Is their stock dropped 25%, and they laid off essentially a large chunk of their data science team in November of this year. Why did they do so? And they exited a huge part of the business that they were in, and that they were not just a website that you can go online and like check home prices, but they also had their own home buying business. So they tried to predict the future home prices, and then they would buy. They would make offers to people. Sort of, you could go to the website. You could, if you own a home, you can like put your home address in Zillow. They would like do some fancy machine learning to predict what the sort of like what the future price of that home will be, and then they'll give you an offer. And so yeah, let me just, I just said this, but let me just put it up again. Is they try to do some prediction for how much it will be worth. They subtract the profit margin. They make an offer for the house, and the seller decides whether or not to accept the offer. And here's the claim. The claim, so I just screenshotted it from a Twitter thread about this, is even if Zillow's model was more accurate than the local agent valuations, local agents or property owners can still beat Zillow on average because they get to choose which houses to buy and sell. So because the way Zillow set up this game is Zillow doesn't get to be strategic. Zillow gets a home address. They do some prediction on whether or not, I mean, like they do some prediction for how much it'll be worth, and then they make an offer. And then the seller gets to be strategic, which given the offer and given what they privately know, they get to be strategic whether or not to accept the offer. And I'm gonna sort of, what I also do want to claim, sort of caveat everything I'm gonna say is like, of course, like real world companies are not so simple that like, you know, like econ Twitter went crazy that of course what I'm about to say is like, of course, why Zillow like failed, of course, like there's no way this could have hoped to succeed. I don't want to make that strong claim. Like Zillow's business model could have succeeded maybe if they'd done something better. I don't know. I also don't know if this is why they failed, as opposed to like maybe they had some true bug in their data science or something, or they didn't follow their data scientists or so on. And I think this is coming out more recently, which is like, I think they had some like business people also overriding their machine learning models. And so I don't want to make too strong of a claim that like, this is why Zillow in particular failed. Because for example, there is still another company called Opendoor, which is much larger, which literally the entire purpose of the company is this business model. And they're still in business. They're still, you know, they're still going strong and claiming that they can do things. So, you know, I don't want to make too strong of a claim. I just want to sort of maybe show you why this test, like if you're going to do a test like this, you do need to be far more careful than just predicting what it'll be worth in the future and then making an offer based on that. So like the straw man I'm going to beat down is this business model, not necessarily what Zillow was actually doing or what Opendoor is doing. Is that enough caveating for me to move on? Okay, great. Okay, and so what's the main idea? Let's do a completely separate toy example. Suppose I have a box, and with equal probability, either there's nothing in the box or there's a cup of coffee in the box. I know what's in the box, and so I got to see inside the box and I know whether it has coffee or not. But you don't know what's in the box. Now, to me, coffee is only worth $1 because I'm not addicted to coffee. But to you, coffee is worth $1.50. And the question is, are we able to make a sale on, like, from me to you on what's in the box? If I can't, like, just open the box and show you whether there's coffee in it. Like, fundamentally, you don't know. So if I can guarantee you that there's coffee in the box, like if I open and show you the box, then you can pay me somewhere in between $1 and $1.50, and we're both happy, right? And exactly where that price ends up between $1 and $1.50 is, like, depending on negotiations and blah, blah, blah. But we're both happy if there's a price anywhere in between that. But if I can't guarantee that there's coffee in the box, what are you going to do? You're going to predict that there's a coffee in the box with probability 0.5. And then your valuation for the box is only 0.75, right? Your valuation is 1.5 divided by 2. And so your valuation for the box is 0.75. And so what is the naive thing? Like in the straw person from the previous slide, the naive thing to do is for you to offer me 75 cents for this box. Because your prediction is that on average, this box is worth 75 cents. But am I going to say yes to your offer? Am I going to say yes to you offering me 75 cents? I'm only going to say yes if there's no coffee in the box, right? I'm going to say no if there is coffee, and I'm going to say yes if there is coffee. Or sorry, if there is not coffee. And so I'm only going to accept the offer if there's no coffee in the box. But y'all are smart people. And so knowing the above, would you ever offer me 75 cents? No, right? Offering me 75 cents is the wrong thing to do. You would offer me $0 because I would only ever accept anything less than $1. I would only ever accept anything if I would only ever accept anything below $1 if you offered me if there was not coffee in there. But if you're smart, but a naive machine learning model would offer me 75 cents anyway, right? And so in this setting, a sale can't happen because to you, the box is only worth at most 75 cents. But for me, I'm only going to give you the box if there's not coffee in there at that price. Are there any questions about this setup? And so the straw person I want to break down from the last slide is the simplified business model I set up was essentially Zillow offering 75 cents anyway. Is like the local agent and the local seller knows a lot more about the house than Zillow does. And so once they have Zillow's offer, they can decide which houses to sell and which houses not to sell. And so this is exactly the sort of, in the chat, someone typed in the market for lemons paper, or said the term markets for lemons, and that's exactly what's going on. Is that if you're naive, is that you end up getting I actually had another slide here that I removed that was actually walking through what the broader thing is like, if this is embedded into a market and you have like 10 of these boxes, some with coffee and some without coffee, then what will end up happening is all the people with coffee will end up leaving the market because like they can't distinguish themselves from someone without coffee. And so that's like the claim that what happens to the used car markets, and that it's impossible to buy a car that's not a lemon, because the only people selling used cars are people who know their used cars are trash or lemons. I'll link to a paper, the original paper that like talks about the markets for lemons idea is like a beautifully read paper. Yeah, so in this analogy, the house is the box that you don't know whether the house is a good house or a bad house. And on average, the machine learning algorithm can predict whether the house is a good house or a bad house. But the local seller, the local real estate agent, knows what's in the house because they have more inside information. So yeah, so that's the exact analogy. Are there any other questions about this analogy? Okay. And so just to summarize this, yes, I just said this without slides, is in the Zillow example, local agents are the ones who can decide whether to sell the box or not after they see the price offered by Zillow and their own evaluation of the quality of the house. And so even if Zillow is better on average for predicting the house prices, the thing is the agents, the people who own the house can see the price that Zillow offers, and so they can update their own mental model for how much the house is worth after they see the quality by Zillow. And so even if the model is correct on average, the sellers being strategic mean that Zillow only gets to buy the houses in which they're wrong. And what I do want to emphasize is that it is possible to mitigate the impact of this strategic behavior. And so in Lily Shu's guest lecture, they had this exact same, they had this poaching setting too, right? Where if you predict where the snares are, and that's where you send the poacher, that's where you send the rangers, then in the next time period, next week, the poachers are just gonna put snares somewhere else. And so the poachers are strategic. And so she talked a little bit about how to modify their machine learning model to take into account this possible strategic behavior. And this is exactly what like algorithms that like chess playing algorithms, Go playing algorithms do, right? They consider opponent's future play. And there's a large ongoing machine learning research thing on a setting called what's called strategic classification, which tries to build machine learning models, classification models, regression models that are robust to this sort of strategic behavior. So even after the strategic behavior happens, the model is accurate on average. And it is possible to mitigate this impact, but you'll never completely eliminate it. So like this is a fundamental limit to how accurate you can get, because if you if the poachers never change where they are, then maybe after 1,000 years you can figure out exactly where the poachers are and you can get perfect accuracy. But if the poachers are randomizing where they are between point A and point B, then you can never get more than 50% accuracy because they're randomizing where they are. And so even if you can modify your algorithm, this is still a fundamental limit to prediction. And so like someone in the chat put up a straw person that, oh, it doesn't science say that much of the world is determinate, that determinism is true. But human strategic behavior just like takes a hammer to that. And that I don't want to make a claim about like quantum determinism and free will and all of that, but the world is effectively stochastic because of strategic behavior. And so no model will ever catch, for example, 100% of poaching behavior. There's a question in the chat. Let's take this offline. I'm not sure I completely understand the question. Okay. And so I do want to take this sort of in the last 7 minutes that we have. I'll give a few time for questions for the class project and so on. But I do want to take this as a call to sort of be far more thoughtful about which tasks that you try to think are good for your machine learning, for your machine learning, that you say, like, oh, I can do this, that, I'm sure I'll do a good job at this task. And so the first question to ask is this task about predicting the future? So if it is, what is the fundamental noise or luck in the outcome to be predicted? Because this fundamental luck factor is a limit to how good of predictions you'll ever get. And if it is about the future, do you believe that, putting luck to the side, that the features that you have actually tell you a lot about the outcome? So it's easy to outsource thinking to the fancy machine learning math model. It's like, oh, they're going to combine all of these 10 covariates to extract a pattern. But just step back and think, is do you actually think these 10 covariates actually, do you actually think that, whether or not, what this interviewer said about this kid at age 9 is actually predictive about this outcome? And if the Fragile Families paper that I said at the beginning seems to suggest that there's actually a this answer is no, a lot more than you might think it is no. And then another heuristic I like, which is this a task that a trained human expert would be good at, right? And so, are you trying to get your machine learning model to do something that even a human that's trained to do it cannot do? And, sometimes the answer is no, humans are not good at this task, but machines would be very good at this task. But if that's the claim, you better make that claim on purpose, right? You better be able to tell me, if I'm someone who does due diligence, I am sometimes does due diligence for VC companies. And this is a question that I would, if you're in front of me trying to pitch something, this is a question I would ask you, right? Is, if this is a task that human experts are not good at, why are humans bad at this task? And why do you hope to believe that a machine learning algorithm could overcome that same problem? On the other hand, if you think a human expert is good at this task, what procedures does that human use? And why can the algorithm hope to mimic or replace those procedures? Right? Are those some things that any of us believe a machine, a non-human could hope to do? And then the last set of questions is the future going to look like the training data? And this could be because of distribution shift. This could be because of strategic reactions to your model. And yeah, so for example, so these are all questions that I would ask a company pitching something to me. Or if the premise of the company is AI predictions about humans. Are there any questions here? Yeah, so the question is, so what the house is, Zillow failed to price in some information that the agents knew. No, so it's actually more subtle than that. What it is the the agents got to see Zillow's prices, and then the agent can update their model. And so yes, it is somewhat that the agents have some potentially some orthogonal information about the current state of the house and so on. But it's actually, it doesn't have to be that the agent is better than Zillow, because Zillow is a company whose business model is around this. It was unlikely the agents were better on average. The problem is that the agents get to see Zillow's prices and then also incorporate their outside information. And so because of that, they can be better than Zillow on average, because they get to see Zillow's prices before making their own predictions. Okay. Yeah, and so there's one more question, which is, if prediction is ill-suited for a task, can we instead take an inference approach to learn as much as we can about a situation to help with operations? And yes, and I think this is exactly right. So I think this is actually one of the takeaways from the sort of that semester, that long class that Matt and Arvind teach, which is you can often use machine learning algorithms as decision support tools, as sort of to help you learn something about a certain part of the feature space as explanatory. And as long as it's not making like the predictions or the decisions by itself. And often it's very good at that. And so this is not saying that never use algorithms, never use AI, never use these sort of techniques. It's know what they're good for and know what they can augment a human for. Okay, so I think that's all I had. I'll stay a few extra minutes if folks had questions about the project or so on. And I'll just keep the announcements up here in the meantime. Okay, I'm going to stop the recording as well.